Hello friends, welcome to this session. Today we are deriving Maxwell's equation. We have previously studied that a static electric field E can exist without a magnetic field H, demonstrated by a capacitor with a static charge Q. Similarly, a conductor with a constant current I has a magnetic field H in the absence of an electric field E. But in case of the time variable fields, E and H, electric field and magnetic field, cannot exist without each other. The valuable work done by James Clerk Maxwell that helped in discovering electromagnetic waves. The time varying fields are involved in experiments of Faraday's, Hertz, and the theoretical analysis done by Maxwell. Maxwell's equations are nothing but a set of four expressions derived from Ampere's circuit law, Faraday's law, Gauss's law, and that Gauss's law for electric field and magnetic field. These expressions, four expressions, can be expressed or can be written in following forms, like the Maxwell's equations are nothing but the equations that describing the relationship between changing the electric and magnetic field. The Maxwell's equations in integral form that govern the independence of fields like E, that is electric field, the D, that is the dielectric constant, or no, it's not the dielectric constant, the isotropic vectors D, then magnetic field, and that magnetic field is associated with the Gauss law, and electric field according to Gauss law, that is the B and H, along with the sources of fields like charge and current associated with different regions in the space like surface and volumes. And the other form, or other hand, the Maxwell's equations in point form, that is referred as a differential form, that explains the characteristics of different field vectors at a given point to each other, as well as the charge and current densities at that point. Basically, the Maxwell's equations are very important quantities or equations, as they are found to be the basic mathematical background for the theory of an electromagnetic waves, transmissions line, and also even study of antennas. Thus, the application of the electromagnetic fields can be very well studied with the Maxwell's equations. So, our aim is to derive the Maxwell's equation for static field first and then for time varying fields. So, today we are discussing the Maxwell's equations for static equations, or for static field initially, and then later on we discuss the differential form or the time varying form. The basic Maxwell's equations for static fields are derived from Faraday's law, Ampere's circuit law, Gauss's law for electrostatic field, and Gauss's law for magnetostatic field. These are the four laws. First, the Faraday's law. Obtained by Faraday's law and Lenz's law of electromagnetic induction. Here, E is the electric intensity, and that measured in the volt per meter. Then second is the Ampere circuit law. That equation obtained by Maxwell's modification of Ampere's law in a circuital form for magnetic field, that field accompanying an electric current H is the magnetic field intensity, that is measured in the ampere per meter, and J is the current density and that is measured in the ampere per meter square. The third one is the Gauss's circuit law for an electrostatic field. Here it is the electric displacement and that is measured in the coulombs per meter square. So the third Maxwell's equation is obtained by with the help of Maxwell's equation, and here the rho is the free charge density in coulomb per meter cube. And fourth one is the Gauss's circuit law for magnetostatic, that is obtained by Maxwell's equation from Gauss's theorem to magnetic field. In this case, B is the magnetic induction and that is measured in the Weber per meter square. So first we derive the Maxwell's equation from Faraday's law. As we know, the closed surface integral EdL is equal to 0. So this is the basic concept from an electrostatic field. The work done over a closed path or a closed counter. Here closed path is nothing but starting point same as terminating point, and that is always 0. Mathematically it is expressed or it is represented as a closed surface integral E is into dl is equal to 0. This equation is called as integral form of Maxwell's equation, that is derived from Faraday's law. This equation, electromagnetic force induced in a closed loop, that is given by E is equal to minus dou phi by dou t. So flux phi is equal to surface integral of BDS. So S is anywhere surface having the loop as a boundary, and the EMF E can be found by calculating the work done in carrying a unit charge that completely around the loop. So that is E is equal to closed integral EdL. As we know, the capital E is the intensity of the electric field that associated with the induced EMF. Therefore, by equating the Fe, first equation and second E equation, we get the closed surface integral E dot dl is equal to 0. Now using the Stokes theorem. The Stokes theorem is used to convert the closed line integral into surface integral. So we get the closed surface integral EdL is equal to surface integral delta cross E into ds. Here the term surface integral del cross E dot ds is 0. But ds cannot be, because S is the vector quantity, cannot be 0. That means del cross E is equal to 0. This equation is called point or differential form of Maxwell's equation derived from Faraday's law for static fields. closed surface integral, it means the equation must be true for any surface, whether small or large in the field. The second equation, that is the Maxwell's equation derived from Faraday's law. Again we are taking the closed surface integral AdL is equal to 0. That gives Maxwell's equation derived from Ampere's circuital law. In this equation, the Maxwell's modified the Ampere's circuital law for the magnetic field accompanying an electric current H. That is the magnetic field intensity in ampere per meter, and J is the current density to amperes per meter square. According to basic concept of magnetostatics in an Ampere circuital law that states that the line integral of magnetic field intensity H around a closed path is exactly equal to the direct current enclosed by that path. It means surface integral H dot dl is equal to I. Here the integral and above expression, or in this expression, should be current enclosed by the different element. Now the current enclosed is equal to the product of current density normal to the closed path and area of closed path. Hence we can write the closed surface integral H dl is equal to surface integral of JDS. Ampere's law in the circuital path, a circuital form that gives the equation. According to this law, the work done in carrying a unit magnetic field or a pole once round a closed arbitrary path linked with the current. That's why we are expressing the closed surface integral H dl is equal to I. Where integral on the right is taken over the surface through which the charge flow corresponding to the current I, and that takes place. Now changing the line integral into surface integral by Stokes theorem. So we get the closed surface integral H dl is equal to surface integral of J dot ds. Now taking the curl to the first side, so by converting the line integral to the surface integral, that is the surface integral H dl is equal to surface integral of del cross H into ds. The above this equation derived from the basis of Ampere's law that stands only for the steady closed current. But the charging electric fields, the current density should be modified. And the modified equation is difficult. That's why we take the curl or the divergence of above equations. So this is the integral form of Maxwell's equation derived from Ampere's circuital law for the static field. Now to relate the H with J, that converting closed line path, closed line integral on LHS, left hand side of the equation, to surface integral by using Stokes theorem. So we get the surface integral H dl is equal to surface integral del cross H into ds. So we get the del cross H is equal to J. Here the divergence of curl H is equal to 0, or divergence of J is equal to 0, which conflicts with the equation of continuity, that is the divergence of J is equal to minus dou rho by dou t. Therefore, Maxwell's realized that the definition of the total current density is incomplete and suggested to add something to J. That's why the equation is Maxwell's derived the equation from Ampere's circuital law with modified equation. The Maxwell's derived third equation from Gauss circuit law. Gauss circuit law for electrostatic field. According to Gauss's law for electrostatic field, the electric flux passing through any closed surface that equals to the total charge enclosed by the surface, that surface. So the psi is equal to closed surface integral d capital D dot ds, that is equal to q, that is the charge, and that charge is enclosed. The most component or the common form to represent Gauss law mathematically is with volume charge density rho v. Hence we can write the closed integral of capital D dot ds is equal to surface integral of volume integral of rho v dv. This equation is called integral form of Maxwell's equation derived from Gauss law for static electric field. To establish the relationship between capital D and rho v, convert the closed surface integral into volume integral by using the divergence theorem. So for this equation we take the divergence by converting closed integral to volume integrals. So closed integral d dot ds is equal to integral integral from volume del dot d is equal to dv. So compare with this equation with this equation. So we get volume integral del dot d dv is equal to volume integral rho v dv. So del dot d is equal to rho into v. When The medium is isotropic. Then the three vectors, that is the D, E and P, are in the same direction, and for small field D is proportional to E. So we can write D is equal to F long into E. So D is the electric displacement. Now the fourth equation in the static field, that is the Gauss's law for magnetostatic field. According to this, again the Gauss's law for the magnetostatic field, the magnetic flux cannot reside in a closed surface due to the non-existence of single magnetic pole. So mathematically we can write the closed integral of B dot ds is equal to 0. This equation is called integral form of Maxwell's equation derived from Gauss's law for the static magnetic field. Now using the divergence theorem, we can write the surface integral of BDS is equal to volume integral of del dot B into dV is equal to 0. So the volume integral del dot B into dV is equal to 0. So divergence or the dV cannot be 0. That means the del dot B is equal to 0. This equation is called point or differential form of Maxwell's equation derived from Gauss law for static field. Here the magnetic lines for the forces are either close or go off to infinity. The number of magnetic lines of forces entering any arbitrary closed surface is exactly the same as leaving it. It means the flux of magnetic induction B across any closed surface is always 0. Now we are discussing the Maxwell's equation for time varying fields. Again the first equation, that is Faraday's law, second Ampere's circuital law, third Gauss's law for electric field, and fourth Gauss's law for magnetic field. Here the Maxwell's equation for time varying fields derived from Faraday's law. Now consider the Faraday's law, which relates the EMF induced in a circuit to the time rate of decrease of total magnetic flux linking the circuit. In general, we can write the closed integral EDL is equal to minus surface integral of dou B by dou T dot ds. This is the Maxwell's equation derived from Faraday's law and is expressed in terms of the total electromotive force EMF induced in a closed path is equal to the negative surface integral of the rate of change of flux density with respect to time over an entire surface bounded by the same closed path. Now using the Stokes theorem, converting line integral of this equation, so surface integral of del cross E into ds is equal to minus surface integral of dou B by dou T into ds. Assuming that the integration is carried out over the same surface on both the sides, we get del cross E is equal to minus dou B by dou T. This is the Maxwell's equation derived from Faraday's law expressed in point form or differential form. The Maxwell's equation for time varying fields derived from Ampere's circuit law. According to Ampere's circuit law, the line integral of magnetic field intensity H around a closed path is equal to the current enclosed by the path. So closed integral H dl is equal to I, that is enclosed to the path, by the path. Replacing current by the surface integral of the conduction current density J over an area bounded by the path of integration of H, we get more general relation as closed integral H dl is equal to surface integral of J dot ds. This equation can be made further general by adding the displacement current density to conduction current density. So closed integral H dl is equal to surface integral J plus dou D by dou T dot ds. So the equation derived from Ampere's circuit law. This equation is an integral form in which line integral of H is carried over the closed path bounding the surface S, over which the integration is carried out on the RHS side, right hand side. In the closed theory or the closed circuit theory of the closed path is called mesh. Hence the equation considered is also mesh equation or mesh relation. So that we can define, or we can giving the statement, the total magnetomotive force around any closed path is equal to the surface integral of the conduction and displacement current densities over the entire surface bounded by the same closed path. So by applying the Stokes theorem to the left hand side, we get surface integral of del cross H into ds is equal to surface integral of J plus dou D by dou T into ds. Assuming that the surface considered for both the integrations is same, so we can write del cross H is equal to J plus dou D by dou T. So this is the point form or differential form of Maxwell's equation derived from Ampere's circuit law. Now deriving the Gauss law for electric field. According to Gauss law, the total flux out of the closed surface is equal to the net charge within the surface. The total flux out of the closed surface is equal to the net charge within the surface, and this can be written as in the integral form, that is surface integral of d capital D in dot ds is equal to the q that is enclosed. If we replaced right hand side by the volume integral of the volume charge density rho v through the volume enclosed by the surface S, considered for integration at left hand side, we get more general form of equation given by the surface integral of dou ds is equal to volume integral of rho v dv. So this equation is Maxwell's equation for electric field derived from Gauss law, expressed in integral form and applied to a finite volume. The statement of this law: the total flux leaving out of a closed surface is equal to the total charge enclosed by a finite volume. So by using the divergence theorem, we can write the volume integral del dot d into dv is equal to volume integral of rho v dv. Assuming the same volume for integration on both the sides, del dot d is equal to rho v. This is the Maxwell's equation for electric fields derived from Gauss law, which is expressed in point form or differential form. The Maxwell's equation derived from Gauss law for magnetic field. So for magnetic field, the surface integral of B over a closed surface S is always 0 due to the non-existence of monopole in the magnetic field. So we can write the surface integral of B dot ds is equal to 0. So this is the magnetic field equation expressed in integral form. This is derived for Gauss law applied to the magnetic field. So we can easily define or give the statement: the surface integral of magnetic flux density over a closed surface is always equal to 0. So using the divergence theorem, the surface integral can be converted to volume integral. So surface integral of del dot b into dv is equal to 0, but being a finite volume, dv is not equal to 0. So del dot b is equal to 0. This is the differential form or point form of Maxwell's equation derived from Gauss's law applied to the magnetic field. Del dot b is equal to 0. This is the summarizes of Maxwell's equation. In first column, here it is differential form. In second column, that is the integral form of Maxwell's equation and corresponding their significance. So first differential form, del cross E is equal to minus dou b by dou t, Faraday's law. Del cross H is equal to J plus dou d by dou t, Ampere's circuital law. Del dot D is equal to rho v. So that is the Gauss law for electric field. Del dot B is equal to 0. There is no isolated magnetic field. For the integral form, closed integral ADL is equal to minus surface integral dou b by dou t into ds. Again it is for related to the Faraday's law. Then closed HDL magnetic field with the line integral is equal to surface integral of J plus dou d by dou t into ds. This is the Ampere's circuital law, that is the modified Ampere's circuital law. Then surface integral of d dot ds, that is the electric displacement, is equal to volume integral of rho dv. This is the Gauss's law for electric field. Then surface integral of b ds is equal to the Gauss's law for magnetic field, that is the no isolated magnetic field. So This is the simple derivation of Maxwell's equation, which is used in electromagnetic energy, antennas. So I hope you understand this Maxwell's equation, derived Maxwell's equation. Thank you for watching this video.